For a nuclear explosion to happen, physics must obey a very specific set of rules. Rules that nuclear reactors were never designed to follow. And yet, millions of people still believe a reactor can explode like a bomb. So today, we ask a deceptively simple question. Can it actually happen? A nuclear weapon is not simply powerful. It is precise. Within a fraction of a second, an enormous amount of fissile material must be forced into what physicists call prompt supercriticality. This is a state where the nuclear chain reaction accelerates uncontrollably, releasing energy faster than the material itself can hold together. Temperatures rise to millions of degrees. Pressure becomes unimaginable. And in an instant, the core tears itself apart. But achieving this is extraordinarily difficult. Nuclear reactors are engineered around a completely different philosophy. Not speed, but control. The fuel inside a typical power reactor is only lightly enriched, usually between 3 and 5% uranium-235. A nuclear weapon, by contrast, requires enrichment levels approaching 90%. Reactors are built to slow neutrons down, using moderators like water. Bombs do the opposite. They rely on fast neutrons to unleash energy all at once. Inside a reactor, control rods stand ready to absorb neutrons, regulating the reaction every moment. Because reactors are engineered for stability, bombs are engineered for chaos. To explode like a nuclear weapon, a reactor would need to overcome several nearly impossible barriers. First, fuel geometry. Reactor fuel is spaced deliberately apart, preventing the rapid assembly required for a detonation. Second, heat. If reactor power begins rising too quickly, temperatures increase, materials expand, and the reaction naturally slows. Physicists call this negative reactivity feedback. It is not just a safety feature. It is physics itself, acting as a stabilizer. In 1986, the world witnessed one of the worst nuclear disasters in history. The explosion at Chernobyl was devastating, but it was not a nuclear detonation. It was a violent steam explosion, triggered by an unstable reactor design and catastrophic operator errors. The RBMK reactor lacked a robust containment structure, allowing radioactive material to escape into the environment. What followed was a graphite fire, not a mushroom cloud. Even in this extreme scenario, the reactor did not explode like a bomb. Today's reactors are designed with layers of safety that earlier generations could scarcely imagine. Passive safety systems can function without human intervention, without external power, guided only by gravity, pressure, and natural circulation. In many designs, the safest state is also the reactor's natural state. To detonate like a weapon, such machines would need to violate the very laws they were built around. Physics is the ultimate safety system. Nuclear energy often inspires fear, partly because its power is difficult to comprehend. But power does not automatically mean danger. Aviation once seemed terrifying. Electricity once felt unnatural. Even the steam engine was feared in its time. Again and again, understanding transformed fear into progress. Nuclear reactors are not dangerous because they are uncontrollable. They are powerful, precisely because we learned how to control them. And perhaps fear begins to fade when understanding begins. This is Reactor Atlas, exploring nuclear energy through physics, not fear.